Picture this. Somewhere in the constellation, Orion, a star 20 times more massive than our Sun, is quietly preparing for the most spectacular death in the known universe. Right now, as you're listening to these words, nuclear furnaces deep within this cosmic giant are flickering, faltering, perhaps even beginning to fail. And when they do, when that final moment arrives, the explosion will be so brilliant it could outshine the full moon in our night sky. You might be able to read a book by its light at midnight. The catch? We have absolutely no idea when this will happen. It could be tomorrow. It could be in 1,000 years. Or, if we're being completely honest about the terrifying beauty of cosmic time, it might have already happened. And the light from that cataclysmic event is racing toward us right now, crossing the vast emptiness of space at 186,000 miles per second. Welcome to a story about stellar death, cosmic violence, and the delicate dance between destruction and distance that keeps our little blue planet safe in an otherwise chaotic universe. I'm here to take you on a journey through some of the most extreme phenomena nature has to offer, where stars don't just fade away quietly like candles in the wind, but rather explode with the force of 10 billion suns, hurling radiation across the galaxy with enough energy to fundamentally alter the chemistry of entire solar systems. This isn't science fiction. This is happening all around us, constantly, in the deep cosmos. And every once in a while, it happens uncomfortably close to home. Before we dive into the heart of this cosmic mystery, I want you to do something for me. Step outside tonight, if you can, and look up at the constellation Orion. It's one of the easiest to spot, that distinctive hourglass shape with 3 bright stars forming the belt across the middle. Now look at the left shoulder of the Hunter, that reddish star that seems to pulse and flicker slightly. That's Betelgeuse, and that gentle, almost friendly-looking point of light is actually a monster. A red supergiant so enormous that if it replaced our Sun, it would swallow Mercury, Venus, Earth, Mars, and stretch out beyond Jupiter's orbit. You're looking at a star that contains more mass than 20 of our suns, compressed into a sphere so large you could fit over 2 billion Earths inside it. And it's dying. But here's where the story gets interesting, where cosmic scales start to bend our minds and challenge our intuitions about time and space. When I say Betelgeuse is dying, I don't mean it in the way we might talk about a tree losing its leaves in autumn, or even a person reaching old age. Stellar death operates on timescales that make human civilization look like a brief flicker. The light you see from Betelgeuse tonight began its journey around the year 1380, during the height of the Black Death in Europe. The photons hitting your retina right now witness the construction of the first windmills, the rise and fall of entire dynasties, the discovery of continents. They've been travelling through the cold vacuum of space for over 600 years, just to reach you in this moment. This brings us to one of the most unsettling aspects of observing the cosmos. We never see things as they are, only as they were. Every star in the night sky is a historical document, a fossil of light preserved in the amber of space-time. And when it comes to Betelgeuse, this temporal disconnect creates a genuinely eerie possibility. The star might have already exploded. The nuclear fires that have burned for millions of years might have already sputtered out. The core might have already collapsed. The shockwave might have already torn through the star's outer layers. And the most brilliant explosion in recorded human history might already be racing toward us through the darkness. We simply wouldn't know until that wall of light and radiation finally arrived. Now, before you start scanning the sky nervously or checking the news for astronomical updates, let me ease your mind with some perspective. Space is big, absurdly, incomprehensibly big. When Douglas Adams wrote that space is really big, he wasn't just being clever, he was touching on something fundamental about cosmic distances that our brains struggle to process. Betelgeuse sits roughly 640 light-years away from Earth. To put that in context, if you could somehow travel at the speed of a commercial airliner, it would take you about 800 million years to reach Betelgeuse. If you walked there, assuming you could walk through the vacuum of space, it would take roughly 15 billion years, longer than the current age of the universe itself. This vast distance is actually our salvation. It's what transforms what would otherwise be a planet-sterilizing catastrophe into merely the most spectacular light show in human history. You see, radiation follows what physicists call the inverse square law, which means that as you double your distance from a source, the intensity of radiation decreases by a factor of 4. Double the distance again, and it decreases by another factor of 4. This isn't just a mathematical curiosity, it's the fundamental principle that allows life to exist in a universe filled with exploding stars. But let's talk about what we would actually see if Betelgeuse exploded tomorrow. The first sign wouldn't be visible light at all. It would be neutrinos, those ghostly particles that barely interact with matter, streaming through the Earth at nearly the speed of light. Modern neutrino detectors around the world would suddenly light up like Christmas trees, registering millions of these ethereal messengers arriving within a 10 to 15 second window. For physicists monitoring these instruments, it would be like receiving a cosmic telegram. Betelgeuse has exploded, light show to follow. A few hours later, when the explosion's shockwave finally reaches the star's outer layers, there would be what astronomers call a breakout of photons. The night sky would suddenly acquire a new star, brilliant beyond anything most humans have ever seen. Betelgeuse would become brighter than Venus, brighter than Jupiter, almost as bright as a full moon, but concentrated into a single, intensely bright point of light. Unlike the gentle, diffused glow of moonlight, this would be an almost uncomfortably brilliant stellar beacon, visible even in broad daylight, casting shadows at midnight, and fundamentally altering the appearance of one of our most recognizable constellations. The visual spectacle would persist for months, gradually fading as all supernovae do, but providing astronomers with an unprecedented opportunity to study stellar death up close. No human in recorded history has witnessed a supernova explosion from a nearby star. The closest we've come was supernova 1987A, which occurred 168,000 light-years away in a neighbouring galaxy. A Betelgeuse supernova would be nearly 300 times closer, offering a level of detail and scientific insight that could revolutionise our understanding of how massive stars die. Recent observations have added new layers of intrigue to the Betelgeuse story. In 2019 and 2020, the star underwent what astronomers dubbed the Great Dimming, suddenly dropping to about 40% of its usual brightness before gradually returning to normal. Initially, many scientists wondered if this was a sign that Betelgeuse was preparing to explode. The dimming event captured public imagination and sparked countless headlines about an imminent supernova. But as often happens in astronomy, the reality turned out to be both more mundane and more fascinating than the initial speculation. The dimming was caused by a massive cloud of dust and stellar debris that temporarily obscured our view of the star. Betelgeuse had essentially sneezed, ejecting a portion of its outer atmosphere that cooled and condensed into dust particles, creating a temporary veil that blocked some of the star's light. This kind of mass ejection is actually quite common for red supergiant stars, which are inherently unstable and regularly shed material into space. But the 2019-2020 event was particularly dramatic, giving us a vivid reminder of just how dynamic and unpredictable these stellar giants can be. Then, in July 2025, astronomers announced a discovery that fundamentally changed our understanding of Betelgeuse. After decades of speculation, they finally confirmed that Betelgeuse is actually part of a binary star system, with a smaller blue-white companion star affectionately nicknamed Beetle Buddy, orbiting the red supergiant. This discovery helps explain some of Betelgeuse's mysterious behaviour, including its regular brightness variations and long-term cycles. It also suggests that Betelgeuse might be younger than previously estimated, potentially pushing back the timeline for its eventual explosion. The binary nature of Betelgeuse had been suspected for years due to unexplained periodic variations in the star's behaviour, including a puzzling 2,070-day cycle that didn't fit with models of a single star. While two groups of astronomers published papers in 2024 suggesting the existence of an unseen companion, it wasn't until 2025 that definitive proof emerged. The companion star had been incredibly difficult to detect because Betelgeuse is so overwhelmingly bright and large that it essentially drowns out any signal from a smaller stellar partner. This brings us to one of the most challenging aspects of predicting when Betelgeuse will explode: the fundamental difficulty of stellar evolution models. Stars are incredibly complex objects, with nuclear processes occurring under extreme conditions of temperature and pressure that we can barely replicate in terrestrial laboratories. The mathematical models that astronomers use to predict stellar evolution involve hundreds of variables and countless assumptions about how matter behaves under these exotic conditions. Current estimates suggest that Betelgeuse will explode somewhere in the time frame of a few 100,000 years from now. But the uncertainty in these predictions is enormous. The star could explode tomorrow, or it could continue burning for another million years. A 2023 research paper challenged previous long-term estimates by suggesting that Betelgeuse might explode within tens of years rather than thousands, based on detailed analysis of the nuclear fusion processes in the star's core. The research focused on the nuclear reactions that enable stars to shine, where simple atoms fuse together to create more complex elements while releasing energy as a byproduct. When a star exhausts its nuclear fuel supply, a supernova explosion becomes inevitable. The study concluded that Betelgeuse appears to be in the late stages of carbon burning, a phase that typically lasts about 1,000 years for a star of Betelgeuse's mass and composition. But here's where recent observations have added a new wrinkle to the story. NASA's James Webb Space Telescope has been providing unprecedented insights into Betelgeuse's current state, with high-resolution infrared images and spectroscopy revealing significant variations in surface temperature, structure, and brightness patterns. These observations have detected what some astronomers describe as symptoms typically associated with the final stages of a massive star's life. The Webb data shows dramatic variations in Betelgeuse's infrared signature, with unusual spikes in surface turbulence and strange pulsations in the star's outer layers. Most intriguingly, the observations seem to suggest possible degradation of Betelgeuse's core structure, which could indicate that the star has begun to exhaust its nuclear fuel supply. This is traditionally considered the final step before gravitational collapse and supernova explosion. Dr. Elena Marquez, the lead astrophysicist studying these Webb observations, has noted something that should give us all pause. She describes what they're witnessing as a level of internal chaos and instability that we've never observed before, comparing the situation to watching Betelgeuse enter its final act. And thanks to Webb's precision, we're watching the curtain rise in real time. These aren't the words of someone engaging in casual scientific speculation. These are the careful, measured observations of a researcher who has spent years studying stellar evolution and is now witnessing something unprecedented. The Webb Telescope's infrared vision allows it to peer through the dust and stellar material that often obscures our view of red supergiant stars, providing a clearer picture of what's happening in Betelgeuse's outer layers, and potentially even offering clues about the nuclear processes occurring deep within the core. What it's revealing is a star in apparent turmoil, with surface features changing on timescales much shorter than astronomers expected, and energy patterns that suggest fundamental changes in the star's internal structure. But here's the thing about cosmic timescales that continues to humble and perplex us. Even with these strong indicators, even with the most advanced telescopes humanity has ever built, imminent in cosmic terms could still mean anywhere from tomorrow to 100,000 years from now. The universe operates on scales that dwarf human comprehension, where 1,000,000 years is considered rapid change and geological epochs pass like seasons. This temporal disconnect creates a fascinating psychological tension. We live in a world where we expect immediate answers, where we can Google any question and receive results in milliseconds, where we track the minute-by-minute changes in weather, stock markets, and social media trends. Yet here we are, staring at a star that might explode at any moment in cosmic terms, but for which any moment could encompass the entire future history of human civilization. Let's step back for a moment and consider what we're really talking about when we discuss stellar explosions. The term supernova has become so familiar that it's easy to lose sight of just how extraordinary these events truly are. When Betelgeuse finally does explode, it will release more energy in a few seconds than our Sun will produce during its entire 10 billion year lifetime. To put this in perspective, if you could somehow capture all the energy humanity has ever used throughout our entire history, from the first fires lit by our earliest ancestors to every power plant, every car, every light bulb that will ever be switched on, that total would represent a tiny fraction of what Betelgeuse will release in the first moments of its death. This energy doesn't just dissipate harmlessly into space, it creates new elements, forging heavy atoms in the incredible temperatures and pressures of the explosion. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of these elements were created in the nuclear furnaces of dying stars and scattered across the galaxy by supernova explosions. In a very real sense, you are made of star stuff, assembled from the ashes of ancient stellar deaths that occurred billions of years before our solar system even existed. But Betelgeuse, for all its spectacular promise, is just one player in a much larger cosmic drama. Our galaxy contains roughly 400 billion stars, and astronomers estimate that a supernova explosion occurs somewhere in the Milky Way approximately every 50 years. Most of these are too distant or obscured by dust to be visible from Earth, but they're happening constantly, a steady drumbeat of stellar death echoing across the galaxy. What makes Betelgeuse special isn't just its size or its proximity, but the fact that we've been watching it closely for so long. It's one of the most studied stars in the sky, observed by generations of astronomers using increasingly sophisticated instruments. We have detailed records of its brightness variations going back centuries, and modern observations have revealed layers of complexity that continue to surprise researchers. The star's variability is particularly intriguing. Unlike our Sun, which maintains a remarkably steady output of energy, Betelgeuse pulses and fluctuates in complex patterns. It has a primary cycle of about 420 days during which its brightness can vary by a factor of 2 or more. There are also shorter cycles of 185 and 230 days, plus that mysterious long-term variation of roughly 2,200 days that we now understand is related to its binary companion. These pulsations aren't just surface phenomena. They reflect fundamental changes happening deep within the star's interior, where nuclear fusion reactions create a delicate balance between the outward pressure of radiation and the inward pull of gravity. As the star ages and its nuclear fuel composition changes, this balance becomes increasingly unstable, leading to the complex variability we observe. Recent computer simulations have provided new insights into what might be happening inside Betelgeuse right now. These models suggest that the star's core has already begun the transition from burning helium to burning heavier elements, like carbon and oxygen. This is a critical phase in stellar evolution because heavier elements burn much faster and less efficiently than hydrogen or helium. It's like switching from burning logs in a fireplace to burning paper. The fuel consumption rate increases dramatically, accelerating the star toward its inevitable end. The carbon burning phase that Betelgeuse appears to be entering typically lasts only about 1,000 years for a star of its mass. After that comes oxygen burning, which lasts mere decades, followed by silicon burning, which lasts only a few years. Finally, the star attempts to burn iron, but iron fusion actually absorbs energy rather than releasing it. When the core fills with iron, the nuclear fires die out completely, and gravitational collapse becomes unavoidable. This is where stellar death becomes truly spectacular. Without the outward pressure of nuclear fusion to support it, the star's core collapses catastrophically. In less than a second, a volume the size of Earth shrinks to a sphere perhaps 20 miles across, reaching densities where a teaspoon of material would weigh as much as Mount Everest. The collapse happens so rapidly that the outer layers of the star initially don't even realize what's happening. But then the shockwave hits. The collapsing core becomes so dense that it rebounds, creating a massive explosion that tears through the star's outer layers at speeds of thousands of miles per second. The energy release is so enormous that for a brief time, the dying star outshines the entire galaxy in which it resides. In the case of Betelgeuse, this explosion will be visible across much of the observable universe, a beacon of stellar death that will announce itself to any civilization with the technology to observe it. Yet even as we discuss these cosmic catastrophes, it's important to remember that stellar death is also stellar birth. The heavy elements created in supernova explosions don't just disappear into space. They become the raw materials for new stars, new planets, and potentially new forms of life. The shock waves from supernova explosions can also trigger the formation of new stars by compressing nearby clouds of gas and dust, setting in motion the gravitational collapse that begins the next generation of stellar evolution. This cosmic recycling process has been ongoing for over 13 billion years, since the first massive stars formed in the early universe and began the process of element creation. The first stars were composed almost entirely of hydrogen and helium, the only elements that existed in significant quantities after the Big Bang. Everything else, every element heavier than lithium, has been created inside stars or during supernova explosions. Our solar system itself is a product of this process. The sun and planets formed from a cloud of gas and dust that had been enriched by numerous previous generations of stellar death. The fact that rocky planets like Earth could form at all is evidence that our region of the galaxy had already experienced multiple rounds of star formation and supernova explosions, building up the inventory of heavy elements necessary for solid worlds. This brings us to a fascinating question that astronomers are still trying to answer. Just how many supernova explosions have occurred in Earth's vicinity over the past few billion years, and what effects might they have had on the development of life on our planet? Scientific evidence suggests that Earth has indeed been affected by relatively nearby stellar explosions in the past. Researchers have discovered trace amounts of a radioactive isotope called Iron-60 in deep-sea sediments from the Pacific Ocean. This isotope has a half-life of only 2.6 million years, which means its presence in recent geological layers indicates that a supernova explosion occurred within the last few million years, at a distance of less than about 100 light-years from Earth. The quantity detected suggests the explosion was close enough to affect our planet, but not so close as to cause a mass extinction event. Some researchers have gone further, proposing links between supernova explosions and specific extinction events in Earth's history. The Pliocene marine megafauna extinction that occurred 2 to 3 million years ago saw up to 1/3 of Earth's large marine species disappear, with extinctions primarily limited to shallow coastal waters rather than affecting deep ocean life. This pattern is consistent with ozone depletion caused by radiation from a distant supernova, which would have increased ultraviolet radiation exposure primarily in surface waters. The mechanism by which supernova can affect life on Earth is both subtle and profound. The primary threat comes not from the initial flash of visible light, but from high-energy radiation, particularly gamma rays and X-rays, that can persist for years after the initial explosion. This radiation doesn't directly harm life on Earth's surface, but it can break apart molecules in our atmosphere, particularly ozone molecules that normally shield us from harmful ultraviolet radiation from the sun. Even a relatively distant supernova, one occurring several hundred light-years away, can produce enough high-energy radiation to reduce Earth's ozone layer by significant amounts. Computer models suggest that a supernova at 160 light-years distance would destroy at least 30% of the ozone layer globally, with polar regions potentially losing up to 87% of their ozone protection. The result would be dramatically increased exposure to ultraviolet radiation, particularly affecting marine ecosystems where phytoplankton form the base of the food chain. But there's another, more insidious effect that can persist for much longer. Within about 100 years following a nearby supernova explosion, Earth would be bombarded by cosmic rays at intensities 20 to 100 times higher than normal levels. These high-energy particles can penetrate deep into the atmosphere and even reach Earth's surface, creating a sustained period of increased radiation exposure that could last for centuries. The increased cosmic ray flux would manifest primarily as moons, penetrating particles that can reach Earth's surface and potentially affect living organisms directly. Recent computational models suggest that radiation doses from moons could increase by factors of 100 or more for extended periods, with the most significant effects occurring in large organisms in the upper ocean, where moon's exceptional penetrating ability would bypass normal biological shielding mechanisms. This paints a picture of a universe that is both more dangerous and more resilient than we might initially imagine. Life on Earth has survived for over 3.5 billion years, despite being periodically bathed in radiation from stellar explosions. The fact that complex life has not only survived but thrived suggests either that these events are rarer than we think, or that life is more adaptable to radiation exposure than current models predict, or perhaps both. But we're not just passive victims of cosmic violence, Earth has several natural protective mechanisms that help mitigate the effects of radiation from stellar explosions. Our planet's magnetic field deflects many charged particles, particularly lower-energy cosmic rays. The atmosphere itself provides substantial shielding from high-energy radiation, and the vast distances between stars mean that even the most energetic explosions are significantly weakened by the time their effects reach us. There's also the matter of magnetic filtering that occurs as radiation travels through interstellar space. Cosmic ray particles, being electrically charged, are deflected by magnetic fields throughout the galaxy. This deflection is more pronounced for lower energy particles, which means that as radiation from a distant supernova travels toward Earth, interstellar magnetic fields naturally filter out some of the most harmful components. Computer simulations that incorporate this magnetic filtering effect show that it significantly reduces the impact of our cosmic ray surges on Earth's atmosphere and biosphere. The effect is similar to how polarized sunglasses filter out certain wavelengths of light, allowing a more manageable portion of the radiation to reach Earth while blocking the most dangerous components. Yet even with all these protective factors, the threat remains real for very close supernova explosions. A supernova occurring at 65 light-years distance would still generate cosmic ray intensities approximately 200 times normal levels, easily overwhelming Earth's natural defences and causing severe ozone depletion that could persist for centuries. Fortunately, such close encounters are extremely rare. Current astronomical surveys have identified all the massive stars within about 50 light-years of Earth, and none of them appear to be in immediate danger of exploding. The closest candidate for a future supernova explosion is Spica, located about 250 light-years away in the constellation Virgo. While Spica will eventually explode as a supernova, it's far enough away that the effects on Earth would be minimal, perhaps noticeable to sensitive instruments, but not dangerous to life. This brings us back to Betelgeuse and the question of cosmic timing. At 640 light-years away, Betelgeuse is comfortably beyond the danger zone for life-threatening effects, but close enough to provide an unprecedented scientific opportunity and spectacular visual display. The question isn't whether Betelgeuse will explode, it's when. And here's where the story takes on an almost philosophical dimension. In our daily lives, we're accustomed to dealing with uncertainty on human timescales. We check weather forecasts, make plans for next week or next year, and generally operate under the assumption that we can predict and control many aspects of our immediate future. But Betelgeuse reminds us that we exist within a much larger cosmic story, one where our most sophisticated scientific instruments and theoretical models can only narrow down the timing of a stellar explosion to within several 100,000 years. This uncertainty isn't a failure of science, it's a fundamental feature of complex systems operating on cosmic scales. Stars are incredibly complicated objects, with nuclear processes occurring under conditions we can barely replicate in terrestrial laboratories. The mathematical models astronomers use to predict stellar evolution involve hundreds of variables and countless assumptions about how matter behaves under these exotic conditions. Even with our best theoretical understanding and most powerful observational tools, predicting exactly when a star will explode remains one of the most challenging problems in astrophysics. It's like trying to predict the exact moment a snowflake will cause an avalanche, or when a single grain of sand will trigger a landslide. We can understand the general processes involved, we can identify the warning signs, but the precise timing remains frustratingly elusive. This brings us to one of the most intriguing aspects of the Betelgeuse story. The possibility that we might be witnessing something truly unprecedented in human history. No person alive today, no one in recorded human history has ever seen a nearby star explode. The closest supernova in modern times, SN 1987A, occurred in a neighbouring galaxy 168,000 light-years away. A Betelgeuse supernova would be nearly 300 times closer, offering a level of detail and scientific insight that could revolutionise our understanding of stellar death. But even more than the scientific value, a Betelgeuse supernova would represent a profound shift in humanity's relationship with the night sky. For thousands of years, the constellation Orion has served as a celestial landmark, helping navigators cross oceans and serving as a seasonal marker for agricultural societies. The distinctive pattern of stars has appeared in mythologies around the world, from ancient Egypt to Aboriginal Australia to the Americas. If Betelgeuse explodes, Orion will never look the same again. The left shoulder of the hunter will blaze with unprecedented brightness for months, fundamentally altering one of our most recognizable star patterns. Future generations will grow up with a different night sky, one marked by the memory of stellar death and the ongoing reminder of cosmic violence. And yet, as we contemplate these cosmic scales and stellar deaths, it's worth remembering that we are not separate from this story. We are part of it, intimately connected to the cycles of stellar birth and death that have shaped the galaxy for billions of years. The carbon in our DNA, the iron in our blood, the calcium in our bones, all of these elements were forged in the nuclear furnaces of dying stars and scattered across space by supernova explosions. In a very real sense, we are the universe becoming aware of itself, temporary arrangements of stellar debris that have somehow achieved consciousness and turned that consciousness back toward the cosmos to contemplate our own origins. When we study Betelgeuse, when we try to predict when it will explode, we're not just observing a distant astronomical event. We're investigating our own deep history, the cosmic processes that made our existence possible. This perspective transforms the question of whether Earth is next from a matter of existential dread into one of cosmic wonder. We're not helpless victims waiting for the universe to destroy us. We're participants in an ongoing story of cosmic evolution, temporary but conscious expressions of the same physical processes that create and destroy stars. The radiation that will someday stream from Betelgeuse's explosion, the same radiation that we've been discussing as a potential threat to life on Earth, is fundamentally the same phenomenon that powers our sun and makes life possible in the first place. It's all electromagnetic radiation, all photons carrying energy across the vast emptiness of space, differing only in intensity and wavelength. This brings us to perhaps the most remarkable aspect of the entire Betelgeuse story, the fact that we can discuss it at all. Here we are on a small rocky planet orbiting an ordinary star in an unremarkable galaxy, somehow able to detect the nuclear processes occurring inside a stellar giant hundreds of light years away, able to predict its eventual fate, and able to calculate the effects its death might have on our own world. The capacity to understand stellar nucleosynthesis, to model the complex physics of core collapse, to predict the propagation of shock waves through stellar atmospheres, represents one of humanity's greatest intellectual achievements. We've essentially reverse-engineered the universe, starting from observations of distant points of light, and working backward to understand the fundamental processes that govern cosmic evolution. And this brings us to a sobering realization about our place in the cosmic order. We exist in what astronomers call the Goldilocks zone, not just of our solar system, but of cosmic history itself. We live in an era when the universe is old enough to have produced the heavy elements necessary for rocky planets and complex chemistry, but young enough that massive stars are still forming and exploding at a manageable rate. Too early in cosmic history, and there wouldn't have been enough heavy elements for planets like Earth to form. Too late, and the universe will have expanded and cooled to the point where new star formation becomes increasingly rare. But let's zoom out even further and consider the broader context of stellar explosions in our galaxy. Betelgeuse may be the most famous supernova candidate, but it's far from the only one. Astronomers have identified dozens of massive stars within a few thousand light-years of Earth that will eventually explode as supernova. Each represents a potential future light show, a cosmic fireworks display that could grace our night skies sometime in the next few million years. One particularly intriguing candidate is Eta Carinae, located about 7,500 light-years away in the southern constellation Carina. This massive stellar system, possibly containing two stars with a combined mass over 150 times that of our Sun, experienced a dramatic eruption in the 1840s that made it temporarily the second brightest star in the sky. The explosion created the beautiful, homunculus nebula, twin lobes of gas and dust expanding outward at nearly 700 kilometers per second. What makes Eta Carinae especially interesting is that it might be what astronomers call a hypernova candidate. These are supernova explosions that occur when extremely massive stars collapse, releasing even more energy than typical supernova and potentially creating the most energetic phenomena in the universe, gamma-ray bursts. Unlike regular supernova, which radiate their energy more or less equally in all directions, hypernovae can focus their energy into narrow jets travelling at nearly the speed of light. This brings us to perhaps the most terrifying scenario in all of astrophysics: a nearby gamma-ray burst pointed directly at Earth. These cosmic death rays represent the most energetic explosions known to occur anywhere in the universe, releasing as much energy in a few seconds as our Sun will produce during its entire 10 billion year lifetime. The gamma radiation from such an event could strip away Earth's ozone layer almost instantly, sterilizing the planet's surface and potentially ending complex life as we know it. Oh, the good news is that gamma-ray bursts are incredibly rare and highly directional. They require very specific conditions. An extremely massive, rapidly rotating star with low metallicity must collapse in just the right way to form the relativistic jets that create the gamma-ray emission. Even then, the jets are so narrow that they would need to be pointed almost directly at Earth to cause significant damage. Current estimates suggest that a gamma-ray burst capable of causing mass extinction on Earth might occur in our galactic neighbourhood, perhaps once every few 100 million years. These timescales are so vast that they dwarf not just human civilization, but the entire evolutionary history of complex life on Earth. The last major extinction event that might have been caused by a gamma-ray burst was the Ordovician-Silurian extinction about 450 million years ago, which eliminated nearly 85% of marine species. But here's where the story becomes both more complex and more fascinating. Recent research suggests that gamma-ray bursts might actually play a positive role in cosmic evolution. The intense radiation from these events can trigger star formation in nearby gas clouds, compress interstellar material, and distribute heavy elements across vast regions of space. In a sense, stellar death becomes a catalyst for stellar birth, continuing the endless cycle of cosmic recycling that has shaped our galaxy for billions of years. This cyclical nature of cosmic violence and creation reflects a deeper truth about the universe. Destruction and creation are not opposites, but rather complementary aspects of the same fundamental processes. The carbon atoms in your body were created in the nuclear furnace of a dying star. The oxygen you breathe was forged during a supernova explosion billions of years ago. The iron in your blood was scattered across space by stellar death and later incorporated into the gas cloud that would eventually collapse to form our solar system. From this perspective, asking whether Earth is next in line for cosmic destruction misses the deeper point. We're not separate from these cosmic processes, waiting to be affected by them. We are these processes, temporary but conscious arrangements of stellar debris that have somehow achieved the remarkable ability to contemplate our own origins and fate. This realization brings with it a profound shift in perspective. Instead of viewing the universe as a hostile environment filled with potential threats, we can begin to see it as the source of our existence, the cosmic theatre in which the drama of consciousness unfolds. The same stellar explosions that might someday threaten life on Earth are the very phenomena that made life possible in the first place. And this brings us to one of the most beautiful paradoxes of our cosmic situation. We exist because stars die. The heavy elements that make rocky planets and complex chemistry possible are created only in the final moments of stellar life, during the incredible temperatures and pressures of supernova explosions. Without stellar death, the universe would contain only hydrogen and helium, and planets like Earth could never have formed. But we also exist despite stellar death. The same processes that created the elements necessary for life also produce radiation and cosmic violence that could potentially destroy that life. We inhabit a narrow window of cosmic conditions, a delicate balance between creation and destruction that has allowed consciousness to emerge and flourish. This balance is maintained by the fundamental structure of space-time itself. The expansion of the universe ensures that most stellar explosions occur at safe distances from any given planet. The inverse square law of radiation ensures that even the most energetic explosions become manageable at sufficient distances. The finite speed of light means that we have advance warning of cosmic events, time to observe and understand them before their effects reach us. In a sense, we live in a universe that is perfectly calibrated for the existence of conscious observers, not because it was designed that way, but because consciousness could only emerge in regions of space-time where these delicate balances are maintained. We don't observe a perfectly safe universe, but we do observe a universe where consciousness is possible, and that possibility requires a very specific set of cosmic conditions. This anthropic principle extends beyond just the balance between creation and destruction. It encompasses the precise values of fundamental constants, the rate of cosmic expansion, the abundance of heavy elements, and countless other factors that must fall within narrow ranges for complex structures like galaxies, stars, planets, and life to exist at all. When we contemplate Betelgeuse and its eventual explosion, we're not just thinking about a single stellar event. We're considering our place within this vast, interconnected web of cosmic relationships that stretches from the quantum realm to the largest structures in the universe. The nuclear processes occurring in Betelgeuse's core right now are governed by the same fundamental forces that shape atomic nuclei, determine the properties of matter, and guide the evolution of the cosmos itself. This interconnectedness extends to time as well as space. The light we see from Betelgeuse tonight began its journey during the late Middle Ages, carrying information about stellar processes that occurred when human civilization was just beginning to develop the scientific methods that would eventually allow us to understand what we were seeing. The elements in our bodies were created billions of years ago in stellar furnaces that exploded long before our solar system existed, their death throes scattering the raw materials for future planets and life across the galaxy. We exist at the intersection of countless cosmic stories, each operating on different timescales, but all fundamentally connected. The story of Betelgeuse is also the story of stellar evolution, which is also the story of element formation, which is also the story of planet formation, which is also the story of the emergence of life and consciousness. These aren't separate narratives, but different chapters in the same vast cosmic epic. And here's perhaps the most remarkable thing about our current moment in cosmic history. We're the first generation of humans to understand these connections. For most of human history, the night sky was a collection of mysterious lights, sources of mythology and navigation, but not understood as physical objects governed by the same laws that operate on Earth. The realization that stars are nuclear furnaces, that they create the elements necessary for life, that their deaths seed the cosmos with the raw materials for future generations of stars and planets. This understanding is less than a century old. We're living through a revolution in cosmic consciousness, a fundamental shift in how we understand our relationship to the universe. This perspective transforms our contemplation of stellar explosions from a matter of fear into one of profound appreciation. When Betelgeuse finally explodes, we won't just be witnessing a spectacular astronomical event. We'll be observing the continuation of the same processes that created us, a cosmic reminder of our deep connection to the stars and the ongoing evolution of the universe itself. The question of whether Earth is next becomes less about survival and more about participation. We're not waiting to be affected by cosmic processes, we're already part of them. Every breath you take involves atoms that were created in stellar explosions. Every heartbeat is powered by nuclear energy that originated in stellar cores. Every thought you think involves complex chemistry that is only possible because of the heavy elements scattered across space by dying stars. From this perspective, the eventual explosion of Betelgeuse represents not a threat but a continuation, another chapter in the ongoing story of cosmic evolution that includes us as conscious participants rather than passive observers. We're not separate from the universe looking in. We're the universe becoming aware of itself. Temporary but remarkable arrangements of stellar matter that have achieved the extraordinary ability to contemplate the very processes that created us. This brings us to a profound question that extends far beyond astronomy. What is our responsibility as conscious beings in a universe capable of such beauty and violence? If we are indeed the universe becoming self-aware, what does that mean for how we should live, how we should treat each other, and how we should approach our brief moment of existence in this vast cosmic story? These are questions that astronomy alone cannot answer, but that astronomical perspective can illuminate. When we truly grasp the scales involved, the vast distances and enormous timescales that separate stellar explosions from their effects on Earth, we begin to see our daily concerns and conflicts in a different light. The political divisions that seem so important, the economic anxieties that keep us awake at night, the social tensions that dominate our news cycles, all of these fade into insignificance against the backdrop of cosmic evolution. This isn't to say that human concerns don't matter, but rather that they matter in a different way than we might initially think. We're not just individuals struggling to survive in an indifferent universe. We're conscious expressions of cosmic evolution, temporary arrangements of stellar debris that have somehow achieved the remarkable ability to understand, appreciate, and even influence the processes that created us. The same nuclear physics that governs stellar explosions also powers our technology, enables our medical treatments, and provides the energy for our civilization. The same electromagnetic radiation that streams from dying stars also carries our communications across the planet and beyond. We're not just observers of cosmic processes, we're participants in them, using our understanding of stellar physics to shape our own destiny and extend our influence beyond the boundaries of our home planet. This participatory relationship with cosmic evolution gives new meaning to our contemplation of events like the eventual explosion of Betelgeuse. We're not just waiting for something to happen to us, we're actively engaged in understanding, predicting, and preparing for cosmic events. Our telescopes and detectors serve as extensions of our senses, allowing us to perceive radiation across the entire electromagnetic spectrum and detect particles that barely interact with matter. When Betelgeuse finally explodes, we'll be ready. Our neutrino detectors will provide advance warning. Our optical telescopes will capture the light show in unprecedented detail. Our space-based instruments will monitor the explosion across multiple wavelengths, providing insights into stellar physics that could revolutionize our understanding of cosmic evolution. More than that, we'll be able to share the experience with the entire human species in real time. The explosion that medieval astronomers would have seen as a mysterious new star in the sky will be understood, documented, and appreciated by billions of people around the world. We'll transform a cosmic accident into a moment of shared wonder and scientific discovery. This transformation of cosmic violence into human understanding represents one of our species' greatest achievements. We've taken a universe that appears indifferent to our existence and found within it the capacity for beauty, meaning, and connection. We've discovered that we're not separate from cosmic processes, but intimately connected to them, that our consciousness emerges from and participates in the same fundamental forces that govern stellar evolution. When we look up at Betelgeuse tonight, we're not just seeing a distant star that might explode someday. We're seeing a mirror that reflects our own cosmic origins, a reminder of the stellar processes that created the elements in our bodies and the nuclear reactions that power our sun. We're seeing a connection that spans hundreds of light years and billions of years, linking our brief moment of consciousness to the vast sweep of cosmic evolution. And in that connection, we find not fear but wonder, not insignificance but meaning, not separation but participation in the grandest story ever told. The story of how the universe created conscious observers capable of understanding and appreciating the very processes that brought them into existence. The explosion of Betelgeuse, when it finally comes, will mark not an ending but a beginning, another chapter in the ongoing story of cosmic evolution, another opportunity for consciousness to witness and understand the beauty and violence of stellar death, another reminder that we are not just in the universe, but that the universe is in us, expressing itself through our wonder, our science, and our capacity to find meaning in the vast darkness between the stars. But what if I told you that the story gets even stranger? What if the greatest threat to Earth doesn't come from the stars we can see, but from the ones we can't? Hidden throughout our galaxy are stellar monsters so exotic, so violent, that they make Betelgeuse look like a gentle campfire by comparison. These are the Wolf-Rayet stars, and they're preparing for explosions that could fundamentally alter the fabric of space-time itself. Picture a star so hot that its surface temperature exceeds 50,000 degrees Celsius, more than 8 times hotter than our Sun. A star so unstable that it's literally tearing itself apart, hurling its outer layers into space at speeds of thousands of kilometers per second. A star so massive that when it dies, it won't just explode, it will create a crack in reality itself, opening doorways to dimensions we barely understand. This is WR104, nicknamed the Pinwheel of Death, and it's pointing directly at us. Located roughly 8,000 light-years away in the constellation Sagittarius, WR104 presents us with a cosmic riddle wrapped in stellar violence. Unlike the relatively stable dance toward death that Betelgeuse performs, Wolf-Rayet stars exist in a state of constant catastrophe. They've already blown away their outer hydrogen layers, exposing the nuclear furnace beneath to the cold vacuum of space. What we see when we look at WR104 isn't really a star in the traditional sense. It's the naked core of a stellar giant, burning helium and heavier elements in plain view. The visual signature of WR104 is unlike anything else in the night sky. Through powerful telescopes, it appears as a perfect spiral, like a cosmic pinwheel frozen in time. But this beautiful pattern masks a terrifying reality. The spiral is created by two massive stars locked in a deadly orbital dance, their stellar winds colliding and creating shockwaves that spiral outward as the system rotates. It's breathtakingly beautiful and utterly deadly, a cosmic ballet performed by objects so massive they bend space-time around them. What makes WR104 particularly unnerving is its orientation. The axis of rotation, the invisible line around which this stellar pinwheel spins, appears to be pointed roughly in Earth's direction. This might seem like an abstract geometric detail, but it has profound implications for our planet's future. When Wolf-Rayet stars explode, they don't just create ordinary supernova. They create something far more dangerous: gamma-ray bursts. Imagine concentrating all the energy our Sun will produce during its entire 10 billion year lifetime and releasing it in just 10 seconds, then focusing that inconceivable amount of energy into two narrow beams travelling at 99% the speed of light. That's a gamma-ray burst, and it represents the most energetic phenomenon known to occur anywhere in the universe. For a brief moment, a gamma-ray burst can outshine entire galaxies, visible across billions of light-years of space. So here we are at the end of our cosmic journey, having peered into the heart of stellar death and emerged with something unexpected, not fear, but wonder. Betelgeuse may explode tomorrow or in 100,000 years, but either way, we'll be here to witness the universe writing another chapter in its endless story of creation through destruction. Until next time, keep looking up, and remember that you are quite literally made of stars. If this cosmic perspective has stirred your curiosity about the universe's most extreme phenomena, you'll want to explore black holes, the quantum realm's deepest and darkest secrets.